The Geiger counter is an instrument used for measuring ionizing radiation, used widely in such applications as radiation dosimetry, radiological protection, experimental physics and the nuclear industry. It detects ionizing radiation, such as alpha particles, beta particles and gamma rays, using the ionization effect produced in a Geiger-Müller tube, which gives its name to the instrument. In wide and prominent use as a handheld radiation survey instrument, it is perhaps one of the world's best-known radiation detection instruments. The original detection principle was discovered in 1908. But it was not until the development of the Geiger-Müller tube in 1928 that the Geiger-Müller counter became a practical instrument. Since then it has been very popular due to its robust sensing element and relatively low cost. However, there are limitations in measuring high radiation rates and the energy of incident radiation. Principle of operation. A Geiger counter consists of a Geiger-Müller tube, the sensing element which detects the radiation, and the processing electronics, which displays the result. The Geiger-Müller tube is filled with an inert gas such as helium, neon, or argon at low pressure, to which a high voltage is applied. The tube briefly conducts electrical charge when a particle or photon of incident radiation makes the gas conductive by ionization. The ionization is considerably amplified within the tube by the Townsend discharge effect to produce an easily measured detection pulse, which is fed to the processing and display electronics. This large pulse from the tube makes the GM counter relatively cheap to manufacture, as the subsequent electronics is greatly simplified. The electronics also generates the high voltage, typically 400 to 600 volts, that has to be applied to the Geiger-Müller tube to enable its operation. The article on the Geiger-Müller tube has a more detailed description of the fundamental ionization mechanism. Readout. There are two types of radiation readout, counts or radiation dose. The counts display is the simplest and is the number of ionizing events displayed either as a count rate, commonly counts per second, or as a total over a set time period. The counts readout is normally used when alpha or beta particles are being detected. More complex to achieve is a display of radiation dose rate, displayed in a unit such as the sievert, which is normally used for measuring gamma or X-ray dose rates. A GM tube can detect the presence of radiation, but not its energy, which influences the radiation's ionizing effect. Consequently, instruments measuring dose rate require the use of an energy-compensated GM tube, so that the dose displayed relates to the counts detected. The electronics will apply known factors to make this conversion, which is specific to each instrument and is determined by design and calibration. The readout can be analog or digital, and increasingly, modern instruments are offering serial communications with a host computer or network. There is usually an option to produce audible clicks representing the number of ionization events detected. This is the distinctive sound normally associated with handheld or portable Geiger counters. The purpose of this is to allow the user to concentrate on manipulation of the instrument whilst retaining auditory feedback on the radiation rate. Limitations. There are two main limitations of the Geiger counter. Because the output pulse from a Geiger-Müller tube is always the same magnitude regardless of the energy of the incident radiation, the tube cannot differentiate between radiation types. A further limitation is the inability to measure high radiation rates due to the dead time of the tube. This is an insensitive period after each ionization of the gas, during which any further incident radiation will not result in a count, and the indicated rate is therefore lower than actual. Typically, the dead time will reduce indicated count rates above about 104 to 105 counts per second depending on the characteristic of the tube being used, whilst some counters have circuitry which can compensate for this. For accurate measurements, ion chamber instruments are preferred for high radiation rates. Types and applications. The application and use of a Geiger counter is dictated entirely by the design of the tube, of which there are a great many, but they can be generally categorized as end window, or windowless, thin-walled, or thick-walled, and sometimes hybrids of these types. Particle detection. The first historical uses of the Geiger principle were for the detection of alpha and beta particles, and the instrument is still used for this purpose today. For alpha particles and low-energy beta particles, the end window type of GM tube has to be used, as these particles have a limited range even in free air, and are easily stopped by a solid material. Therefore, the tube requires a window which is thin enough to allow as many as possible of these particles through to the fill gas. The window is usually made of mica with a density of about 1.5–2.0 mg per square centimeter. Alpha particles have the shortest range, and to detect these the window should ideally be within 10 mm of the radiation source due to alpha particle attenuation in free air. However, the GM tube produces a pulse output which is the same magnitude for all detected radiation, so a Geiger counter with an end window tube cannot distinguish between alpha and beta particles. A skilled operator can use distance to differentiate alpha and high-energy beta, but with the detector in close contact with the radiation source the types are indistinguishable. The pancake Geiger Müller detector is a variant of the end window probe, but designed with a larger detection area to make checking quicker. However, the pressure of the atmosphere against the low pressure of the fill gas limits the window size due to the limited strength of the window membrane. High-energy beta particles can also be detected by a thin-walled, windowless GM tube, which has no end window. Although the tube walls have a greater stopping power than a thin end window, they still allow these more energetic particles to reach the fill gas. End window GM detectors are still used as a general-purpose portable radioactive contamination measurement and detection instrument. Owing to their relatively low cost, robustness and their relatively high detection efficiency, particularly with high-energy beta particles. However, for discrimination between alpha and beta particles or provision of particle energy information, scintillation counters or proportional counters should be used. Those instrument types are manufactured with much larger detector areas, which means that checking for surface contamination is quicker than with a GM instrument. Gamma and X-ray detection. Geiger counters are widely used to detect gamma radiation, and for this the windowless tube is used. However, efficiency is generally low due to the poor interaction of gamma rays compared with alpha and beta particles. For instance, a chrome steel GM tube is only about 1% efficient over a wide range of energies. The article on the Geiger Müller tube carries a more detailed account of the techniques used to detect photon radiation. For high-energy gamma, it largely relies on interaction of the photon radiation with the tube wall material, usually 1 to 2 mm of chrome steel on the thick-walled tube, to produce electrons within the wall which can enter and ionize the fill gas. This is necessary as the low-pressure gas in the tube has little interaction with high-energy gamma photons. However, for low-energy photons there is greater gas interaction and the direct gas ionization effect increases. With decreasing energy, the wall effect gives way to a combination of wall effect and direct ionization, until direct gas ionization dominates. Due to the variance in response to different photon energies, windowless tubes employ what is known as energy compensation, which attempts to compensate for these variations over a large energy range. Low-energy photon radiation such as low-energy X-rays or gamma rays interacts better with the fill gas. Consequently, a typical design for low-energy photon detection for these is a long tube with a thin wall or with an end window. The tube has a larger gas volume than a steel-walled tube to give an increased chance of particle interaction. Neutron detection. A variation of the Geiger tube is used to measure neutrons. where the gas uses boron trifluoride or helium-3 and a plastic moderator is used to slow the neutrons. This creates an alpha particle inside the detector and thus neutrons can be counted. Gamma measurement, personnel protection and process control. The term Geiger counter is commonly used to mean a handheld survey-type meter. However, the Geiger principle is in wide use in installed area gamma alarms for personnel protection, and in process measurement and interlock applications. A Geiger tube is still the sensing device, but the processing electronics will have a higher degree of sophistication and reliability than that used in a handheld survey meter. Physical design for handheld units. There are two fundamental physical configurations: the integral unit with both detector and electronics in the same unit, and the two-piece design which has a separate detector probe and an electronics module connected by a short cable. The integral unit allows single-handed operation, so the operator can use the other hand for personal security in challenging monitoring positions. But the two-piece design allows easier manipulation of the detector, and is commonly used for alpha and beta surface contamination monitoring where careful manipulation of the probe is required or the weight of the electronics module would make operation unwieldy. A number of different sized detectors are available to suit particular situations, such as placing the probe in small apertures or confined spaces. Gamma and X-ray detectors generally use an integral design, so the Geiger-Müller tube is conveniently within the electronics enclosure. This can easily be achieved because the casing usually has little attenuation, and is employed in ambient gamma measurements where distance from the source of radiation is not a significant factor. However, to facilitate more localized measurements such as surface dose, the position of the tube in the enclosure is sometimes indicated by targets on the enclosure, so an accurate measurement can be made with the tube at the correct orientation and a known distance from the surface. There is a particular type of gamma instrument known as a hotspot detector, which has the detector tube on the end of a long pole or flexible conduit. These are used to measure high radiation gamma locations whilst protecting the operator by means of distance shielding. Particle detection of alpha and beta can be used in both integral and two-piece designs. A pancake probe is generally used to increase the area of detection in two-piece instruments whilst being relatively lightweight. In integral instruments using an end window tube, there is a window in the body of the casing to prevent shielding of particles. There are also hybrid instruments which have a separate probe for particle detection and a gamma detection tube within the electronics module. The detectors are switchable by the operator, depending the radiation type that is being measured. Guidance on application use. In the United Kingdom, the House has issued a user guidance note on selecting the best portable instrument type for the radiation measurement application concerned. This covers all radiation protection instrument technologies and is a useful comparative guide to the use of GM detectors. The guide does not recommend the GM detector for mixed alpha and beta contamination detection, and they are only recommended as satisfactory for beta-only contamination. However, for gamma and low-voltage X-rays they are recommended as the best instrument type. History. In 1908, Hans Geiger, under the supervision of Ernest Rutherford at the Victoria University of Manchester, developed an experimental technique for detecting alpha particles that would later be used in the Geiger-Müller tube. This early counter was only capable of detecting alpha particles and was part of a larger experimental apparatus. The fundamental ionization mechanism used was discovered by John Seely Townsend by his work between 1897 and 1901, and is known as the Townsend discharge, which is the ionization of molecules by ion impact. It was not until 1928 that Geiger and Walther Müller developed the sealed Geiger-Müller tube, which developed the basic ionization principles previously used experimentally. This was relatively small and rugged, and could detect more types of ionizing radiation. Now a practical radiation instrument could be produced relatively cheaply, and so the Geiger-Müller counter was born. As the tube output required little electronic processing, a distinct advantage in the thermionic valve era due to minimal valve count and low power consumption, the instrument achieved great popularity as a portable radiation detector. Modern versions of the Geiger counter use the halogen tube invented in 1947 by Sidney H. Leibson. It superseded the earlier Geiger tube because of its much longer life and lower operating voltage, typically 400 to 600 volts. Gallery. Use of a hotspot detector on a long pole to survey waste casks. GM pancake detector feeding a microcontroller data log or sending data to a PC via Bluetooth. A radioactive rock was placed on top the GM, causing the graph to rise. GM counters being used as gamma survey monitors, seeking radioactive satellite debris.